pop. 5 days ago, the ground beneath the eastern North Island of New Zealand moved hard enough to be detected across several international seismic networks. Early global estimates put the event close to magnitude 5.9. New Zealand's own monitoring settled near magnitude 5.7. That difference is normal after an earthquake because agencies use different stations, magnitude scales, and processing methods. Plain. What matters more than the decimal point is where this earthquake happened, close to the East Cape and the northern end of the Hikurangi plate boundary. One of the most closely watched seismic regions in the country, that location changes the story. A magnitude 5.7 earthquake is strong enough to be widely felt, but it is not automatically evidence that a much larger earthquake is beginning. New Zealand experiences many earthquakes because the country sits across the boundary between the Pacific and Australian plates. Crust. Others occur inside the descending Pacific plate. Still others happen directly on the plate interface. The August 2nd event was deep enough that scientists cannot honestly describe it as the Hikurangi megathrust itself rupturing based on location alone. Plain. And that is the first correction this story needs. The earthquake happened within the broader Hikurangi system, but proximity is not proof of connection to the locked part of the megathrust pack. It is possible for a moderate earthquake in this region to come from a fault inside the subducting slab, while the plate boundary above or below it remains locked. That distinction may sound technical, yet it separates real seismic hazard from the much more dramatic claim that a giant rupture has started. Craft. The Hikurangi subduction zone runs offshore along the east coast of the North Island, from near Gisborne toward the top of the South Island plain. Here, the Pacific plate dives beneath the Australian plate. New Zealand researchers describe Hikurangi as the country's largest and most active fault system. Plains. The northern and central sections regularly host slow slip events, where parts of the boundary move over days or weeks instead of breaking in seconds. Farther south, portions of the interface are more strongly locked and capable of storing strain for much larger earthquakes. Ports. So when a strong earthquake appears near East Cape, the location deserves attention even if the event itself is not extraordinary. By New Zealand standards, the temptation is to turn every noticeable earthquake into a warning. Park. That is exactly what the evidence does not support. There is no scientific method that can take one magnitude 5.7 event and convert it into a countdown to a magnitude 8 earthquake. Scientists can estimate long-term probabilities. They can map where faults are locked, air. They can detect slow slip, tremor, and clusters of ordinary earthquakes. But they cannot name the day, hour, or exact location of the next major rupture. What they can do is understand the system better each time it moves. The northern Hikurangi margin is unusual because the subducting Pacific plate carries thick, rough oceanic crust toward New Zealand. Piece amounts, ridges, sediment, fluids, and fractures are dragged into the subduction zone. All of those features influence where stress accumulates and where it is released. Some parts of the boundary creep, some host slow earthquakes, some appear capable of remaining locked for long periods. That mixed behavior is one reason Hikurangi has become a natural laboratory for earthquake science. Researchers have placed instruments on land and on the seafloor to observe motions that would otherwise be invisible. Continuous GNSS stations can measure coastlines shifting by millimeters or centimeters during slow slip events. Ocean bottom pressure sensors and seismometers extend those observations closer to the offshore plate boundary. Seismic imaging allows scientists to infer where fluids, faults, and changing rock properties may affect slip behavior at depth. Now place the August earthquake back into that picture. International Solutions located the event beneath or near the East Cape region, with reported depths ranging from several tens of kilometers depending on the network. That is deeper than the shallow offshore megathrust near the trench. In this part of New Zealand, earthquakes can occur within the descending slab as it bends and sinks beneath the North Island. Those intraslab events can be strong and widely felt without meaning that the main Hikurangi interface has broken. This is the ordinary interpretation that needs to collapse. A quake near a dangerous fault is not automatically a quake on that dangerous fault, but the opposite mistake is also possible. Saying the event does not prove a megathrust rupture is not the same as saying the region is unimportant. Hikurangi is a major source of New Zealand's long-term earthquake and tsunami risk. The southern portion alone has been assigned roughly a 1 in 4 chance of producing a magnitude 8 class subduction earthquake within 50 years in published New Zealand research. That probability is not a prediction. It is a long-term hazard estimate built from geological evidence of past ruptures. The new earthquake did not create that hazard. It happened inside a landscape where the hazard already exists. That is why scientists care about the exact depth, mechanism, and relationship of earthquakes like this, one to the plate boundary. A moderate earthquake is not a warning siren for the next giant rupture. pressure. It is a data point inside, one of the most complicated plate boundary systems on Earth. To understand why that distinction matters, we have to go beneath the North Island and follow the Pacific Plate as it disappears into the mantle. There is also a human reason to resist overclaiming. East Coast communities have lived with repeated earthquakes, tsunami, education, and evacuation planning for years. Pox. An exaggerated headline may attract attention once, but it can blur the difference between a routine seismic event and the natural warning signs that require immediate action. The more dangerous the permanent hazard, the more important it becomes to keep those categories clear. A moderate earthquake near Hikurangi is meaningful because of where it occurred and what scientists can learn from it, not because fear requires us to promote it into a precursor. At the surface, New Zealand looks like two long islands separated by Cook Strait. At depth, it is a plate boundary machine whose geometry changes from one end of the country to the other. North and east of the North Island, the Pacific Plate moves toward New Zealand and is forced beneath the Australian Plate. The boundary between them forms the Hikurangi subduction zone. Farther south, the plate motion is transferred into the Marlborough Fault system and then into the Alpine Fault, the huge strike-slip structure that runs along the spine of the South Island. To the southwest, subduction begins again in Fiordland and the Puisaga region. That changing geometry explains why the same magnitude earthquake can mean different things in different parts of the country. PA. Near East Cape, the Pacific Plate is descending beneath the North Island at a relatively shallow angle before it bends more steeply at depth. The slab is not smooth. It contains inherited fractures and structures formed when the oceanic plate was created and later bent at the trench. As those faults are pushed deeper, pressure and temperature change. Some can reactivate and produce earthquakes inside the slab itself. These are called intraslab earthquakes. Planes. They are different from megathrust earthquakes. A megathrust event occurs on the contact between the two plates, where enormous areas of the interface can rupture together. An intraslab earthquake happens inside one of the plates, usually across a much smaller fault. Both can produce strong shaking, but they tell scientists different things about where the rock actually failed. Pox. That difference is central to the August 2nd event. Its depth estimates place it far enough beneath the region that it cannot simply be labeled a shallow rupture of the Hikurangi interface. PAC. Without a full mechanism and local analysis, the scientifically responsible description is that it occurred within the broader Hikurangi subduction environment. The earthquake may illuminate stress in the descending plate, but it does not demonstrate that the locked megathrust is releasing. Pets. This is where the word near matters. A title can be dramatic and still be precise. The event happened near one of New Zealand's most dangerous fault systems. It did not prove that system itself ruptured. Prox. The Hikurangi interface has another behavior that makes it especially fascinating. Parts of it move in slow slip events. Pralf. Instead of producing seconds of violent shaking, a section of the fault can slip over days, weeks, or even months. The total motion may be equivalent to a large earthquake, yet people feel nothing because the energy is released too slowly to generate destructive seismic waves. Northern Hikurangi is one of the best observed slow slip regions in the world. Researchers have documented shallow, slow slip events recurring roughly every 1 to 2 years in parts of the northern and central margin. Coastal GNSS stations can move several centimeters during the largest episodes. Because the offshore plate interface lies beneath the sea, scientists have increasingly deployed instruments on the seafloor to see more directly how the fault behaves where land-based measurements become less precise. Slow slip does not mean the fault is safe. It also does not mean a large earthquake is imminent. Instead, it reveals that different patches of the same plate boundary can have very different frictional behavior. Some slide gradually, some remain locked, some alternate between modes. Fluids moving through the fault zone, the type of sediment entering the trench, roughness on the subducting plate, and the temperature and pressure conditions at depth can all influence how a patch behaves. That complexity is why single earthquake interpretations are dangerous. Imagine a moderate quake occurring inside the slab while a nearby slow slip event is also underway. Those two processes may occupy the same broad tectonic region but still represent different faults and different styles of motion. Scientists would examine whether timing, stress changes, or spatial patterns suggest any relationship. They would not assume a causal connection just because the events happened close together on a map. The same rule applies to the August 2nd quake. The event gives researchers another opportunity to refine the three-dimensional picture beneath East Cape. They can compare its location with the mapped plate interface. They can examine the direction of faulting, PA. They can look for aftershocks and changes in seismicity. They can check GNSS records for any unusual surface deformation. If nothing exceptional follows, that is information too. Most earthquakes do not become the beginning of a larger sequence. Aftershocks normally decrease with time, air. Some sequences contain a larger earthquake later, but there is no reliable way to look at one moderate event and declare that outcome in advance. The proper scientific question is not, is the big one next? It is, what does this event reveal about the fault system that produced it? Hikurangi makes that question especially important because its historical record is short compared with the timescales of the largest earthquakes. New Zealand's written record covers only a small fraction of a typical megathrust earthquake cycle. To understand the bigger events, scientists have to read evidence left in coastal sediments, uplifted shorelines, tsunami deposits, and changes in land level. That geological record points to repeated large subduction earthquakes long before modern instruments existed. The result is a system with two very different clocks. One clock runs in real time, individual earthquakes, slow slip, tremor, and millimeter scale deformation measured every day. The other runs across centuries, the accumulation and release of strain capable of producing magnitude 8 class earthquakes and tsunamis. The August quake belongs to the first clock. The danger people associate with Hikurangi comes from the second. The challenge for scientists is to understand how those clocks interact without pretending that one moderate earthquake can tell us when the long one will strike. One useful way to visualize the geometry is to imagine the North Island resting above a huge descending sheet. Near the trench, that sheet lies relatively shallow. Moving inland, it dives deeper beneath the land. Earthquakes can occur above the sheet, on the contact surface, or inside the sheet itself. Two epicenters, separated by only a few kilometers on a flat map, can therefore belong to very different structures. That is why depth is not a minor technical number attached to an earthquake report. It is one of the clues that tells scientists which part of the tectonic machine moved. The reason Hikurangi carries so much weight in New Zealand's hazard planning is not that every earthquake there becomes catastrophic plains. It is that the plate boundary is capable of earthquakes on a completely different scale. New Zealand researchers describe the Hikurangi subduction zone as the country's largest fault. Credible, full margin rupture could reach the high magnitude 8 range, with shaking lasting far longer than a typical moderate earthquake, and with the potential to generate a major local tsunami. Emergency planning scenarios are built around those possibilities, because waiting until such an event begins would be far too late to start thinking about consequences. That does not turn the August 2nd quake into a warning. It puts the quake in context. The magnitude scale itself helps explain why. Magnitude is logarithmic. An increase of one whole magnitude represents roughly 32 times more energy release. A magnitude 8 earthquake is therefore not simply a somewhat larger version of a magnitude 5.7. The rupture area, duration, and total energy can be orders of magnitude greater. This matters because viewers often see the number 5.7 and imagine it as a percentage of an 8. It is not. A moderate earthquake may rupture a fault patch measured in kilometers. A great subduction earthquake can rupture hundreds of kilometers of plate boundary. The physical scale is fundamentally different. Hikurangi's geological record shows that large earthquakes have happened before. Coastal studies along the southern margin have identified evidence consistent with repeated subduction earthquakes over thousands of years. One line of research estimates roughly a 26% chance of a magnitude 8 or larger earthquake on the southern Hikurangi margin within the next 50 years. That number deserves careful handling. 26% does not mean the fault is 26% ready. It does not mean the risk rises in a straight line every year. It does not mean an earthquake is due on a schedule. 0.7. It certainly does not mean the August magnitude 5.7 has moved a countdown closer to zero. It means that when scientists combine geological recurrence evidence with uncertainty, about one scenario in 4 within that 50-year window contains a large rupture pack that is serious enough on its own, and there is no need to exaggerate it. The tsunami component makes the hazard even more distinctive because Hikurangi sits close to the east coast. Parts of the seafloor could rise or fall quickly enough to displace the ocean. For some communities, damaging waves from a local source can arrive in minutes to tens of minutes. That is why New Zealand's public guidance emphasizes natural warning signs such as shaking that is long or strong. Again, none of that guidance was created because of the August 2nd event. It exists because the region has a permanent tectonic risk. This is the useful reframe. Monitoring. A dangerous fault is not evidence that scientists think disaster is imminent. Monitoring is what allows a country with permanent seismic risk to understand ordinary movement, recognize unusual changes, improve hazard models, and make faster decisions when a genuinely damaging event occurs. AirGeoNet is central to that process. The network brings together seismometers, strong motion instruments, GNSS stations, volcano sensors, and other geophysical data. Every moderate quake improves the catalog. Every revised location helps map where active structures sit in 3 dimensions. Felt reports add information about how shaking spreads through different ground conditions and building environments. That data becomes especially valuable in eastern North Island because several earthquake sources overlap. There is the plate interface itself, along with faults inside the subducting Pacific plate. There are also upper plate faults within the Australian plate and separate slow slip regions. And farther south, the system transitions toward major strike slip faults across Wairarapa, Wellington, and Marlborough. ADOT on an earthquake map does not tell you which of those sources ruptured. Depth and mechanism do. This is why early international earthquake reports can differ. One network may estimate a magnitude of 5.9 at a shallow preliminary depth. Another, using denser local stations, may locate the event deeper and revise the magnitude. That does not mean one agency is hiding something or that the earthquake changed after it happened. It means earthquake parameters are estimates that improve as more waveforms are processed. For a New Zealand event, the local GeoNet solution is normally the most relevant operational reference because its station network is designed around the country's tectonic environment. The August event offers a clean example of why that matters. The initial global headline centered on magnitude 5.9, the local number settled lower, near 5.7, with a deeper source. That change affects how the event should be framed. A deeper earthquake beneath the Hikurangi margin has a different interpretation from a shallow rupture on the offshore plate boundary. The risk is still real. The story is simply different. Instead of a dangerous megathrust just broke, the stronger evidence-based story is a noticeable earthquake occurred inside, one of the most complex and hazardous plate boundary regions on Earth, and its depth shows why location alone can mislead. That gives us a better question. What are scientists actually watching now? They are not watching for a mystical precursor pattern. They are watching measurable things: the aftershock distribution, the location of slip, the focal mechanism, slow slip activity, crustal deformation, and any change that falls outside normal background behavior. If those measurements remain ordinary, the earthquake becomes another valuable entry in the long-term record. If something unusual appears, scientists have the instruments to see it. That is the real value of living above a monitored fault system. The danger does not disappear, but uncertainty becomes measurable instead of imaginary. The 1947 Gisborne area tsunami earthquakes show why scientists also care about the style of rupture, not simply magnitude. Those historical events generated unusually large local tsunami relative to the shaking people felt, illustrating that a shallow offshore source can pose a very different threat from a deeper inland or intraslab earthquake of similar numerical magnitude. The August event should not be compared directly with those earthquakes, as though the mechanisms were the same. Their value here is to show that the Hikurangi margin contains multiple earthquake behaviors, each with a different hazard signature. By the time most people hear about a moderate earthquake, the most important scientific work has already begun. Seismic waves arrive at stations across New Zealand within seconds. Automated systems estimate the location and magnitude. As more data arrive, those estimates are revised. Planes compare the event with known faults and the modeled surface of the subducting plate. Aftershocks begin filling in the geometry of the rupture. GNSS stations are checked for any measurable permanent movement. For the August 2nd earthquake, that process matters more than the first headline number. The international magnitude 5.9 estimate captured the event quickly. The local New Zealand solution placed it closer to 5.7. That may appear like a small revision, but it is a reminder that the first version of an earthquake is not the final geological interpretation. The title, therefore, has to change with the evidence. Calling it M5.7 after the local network has refined the event would preserve a stronger number at the cost of accuracy. Saying it just happened 5 days later would also stretch a temporal claim that was true only in the immediate aftermath. And saying the dangerous Hikurangi fault itself ruptured would go beyond what the location alone proves. The corrected story is still powerful. Strong M5.7 earthquake shook near one of New Zealand's most dangerous fault zones. It happened beneath the East Cape region, inside the broad plate boundary environment where the Pacific plate dives beneath the North Island plains. That zone contains shallow, slow slip patches, deeper intraslab faults, strongly coupled regions, and one of the country's largest sources of long-term earthquake and tsunami risk. But no single moderate quake unlocks the future. That boundary is worth repeating, because earthquakes attract prediction language faster than almost any other natural hazard. A cluster appears, and people ask whether stress is being transferred. Moderate quake hits near a famous fault, and social media declares that the big one is next. A slow slip event is detected, and it is described as the fault waking up. Those phrases can sound scientific while saying more than the measurements allow. Earthquakes do change stress around a rupture. Larger earthquakes can trigger seismicity elsewhere. Slow slip can interact with ordinary earthquakes. Those physical facts do not provide a reliable clock for the next great earthquake. The Earth's crust contains too many interacting faults, too much three-dimensional structure, and too much uncertainty in the frictional state of each patch. That is why long-term probability and short-term prediction must stay separate. The roughly 1 in 4 50-year estimate for a magnitude 8 class southern Hikurangi earthquake is a long-term hazard calculation planes. It exists independently of the August 2nd magnitude 5.7. The moderate earthquake neither proves nor cancels that risk. What it does is add information. If its aftershocks define a previously poorly resolved structure inside the slab, scientists learn more about how the Pacific plate is deforming. If its mechanism matches known intraslab faulting, that strengthens the interpretation. If GNSS records show no unusual deformation on the plate interface, that becomes an important negative observation. If nearby slow slip behavior changes, researchers can investigate whether the timing is meaningful or coincidental. Science advances through those details, not through a dramatic label. People living along the East Coast, the practical lesson is also broader than this. One event. New Zealand's official earthquake and tsunami guidance is built around a hazard that is always present. During shaking, drop, cover, and hold. Near the coast, if an earthquake is long or strong, move to high ground or inland without waiting for an official tsunami message. Those instructions are designed for the rare event when minutes matter. The August quake did not create a new emergency. Planes. It is a reminder of why the system exists. There is something almost deceptive about the Hikurangi margin when the weather is calm. The fault itself is offshore and mostly invisible. There is no giant crack running along the beach. Much of its motion happens deep beneath the sea and beneath the North Island. Slow slip episodes can move parts of the coast by centimeters without anyone feeling a thing. Then a moderate earthquake arrives and briefly makes the plate boundary visible, not because it reveals when the next great earthquake will happen, because it reminds us that the machinery is always moving. That is the final image to hold on to. East of the North Island, the Pacific plate continues sliding beneath New Zealand at rates measured in centimeters per year. Along the boundary, some patches creep, some slip slowly, and some remain locked. Or deeper down, faults inside the descending slab can rupture and send shaking through the country. The August 2nd earthquake was one of those moments when that hidden system announced itself. Its magnitude matters, its depth matters more, and its location matters most of all, because it sits beside a fault system capable of events vastly larger than the one people just felt. But the scientifically honest conclusion is not that a disaster is coming. It is that New Zealand already knows where one of its greatest long-term earthquake hazards lies, and every well-measured earthquake helps scientists see that hidden boundary more clearly. The ground has gone quiet again. The plate boundary has not. That monitoring philosophy is increasingly reflected in national hazard modeling. New Zealand's seismic hazard framework does not rely on one famous fault or one recent earthquake. It combines many known sources, background seismicity, ground motion behavior, and uncertainties about hidden faults. Hikurangi is a major contributor, but it sits inside a national network of interacting hazards. The August earthquake, therefore, becomes useful not because it rewrites the national risk picture, but because it gives scientists another real observation against which those models can be tested and improved.